Hello and welcome to Chapter 4, Module 4. In this chapter, we will be covering the first chapter of a series of 3 chapters on Newton's laws. The first one is called Newton's Laws of Motion, which are basically the 3 laws. And then the following chapter, Chapter 5, we will be covering applications of that. So basically, we'll be studying the theory of the laws here, and then we will be applying those laws to real-life application in Chapter 5. And then in Chapter 6, we'll be studying further law, very important law, which is the law of gravitation and circular motion. This is all attributed to Isaac Newton. So up to this point, up to Chapter 3, Chapter 1, 2, and 3, we have been studying the subject of what we call kinematics. And I think I talked to you about what kinematics means. Kinematics means you are studying the motion without asking what caused the motion. This is important in the study of mechanics. So you are basically studying the motion. Say, for example, given the initial velocity of an object right now, what is its position after, say, 2 minutes? Or what is the height of a projectile given its initial velocity? What is its height after 2 seconds? What is the maximum height? And so on. So we basically here, you're asking about kinematic variables, okay? But you never ask about what caused the motion from the first place, you see what I'm saying? And what caused the motion is what we refer to as forces, okay? The force. And so once you start asking what caused the motion, you're no longer talking about kinematics, you're talking about dynamics. So dynamics means you're asking a question, what caused the motion, and how do I quantify this cause, okay? So anyway, we have a general term for that cause of the motion. We refer to it as the force, okay? So what is a force? A force, let me go back to my note. Chapter 4, Newton's Laws of Motion. So we begin with the study of the word force. Basically, the whole chapter really is concentrating on this word, the force. What is the force? The force is an action, or maybe I should say an action, that changes the state of motion of an object. What does that mean? Let's say you have a book sitting on the table. So here is the surface of the table. Here is the book sitting on it, okay? And I ask the question, what is the state of the book? The state of the book right now is at rest, right? We say it's at rest, or the speed or the velocity of the book is equal to 0 initially, okay? So this is at time equals 0. Initially, the state of the book is in the state of rest. You see what I'm saying? However, now, how do I make it move? How do I cause it to move? Well, the only way that I can make it to move is to push it or pull it or lift it or something like that, right? Well, all these words, push, lift, and pull, are expressions of force. So when I say pull it, let's say this way, with a force, we're going to call it F. So when I pull it with this force F, I have changed the state of motion of the object. So I have changed it from the state of rest to the state of motion. So what does the force do? The force is an action, go back to the statement, that changes the state of motion of the object. Now you understand it, I hope. You see what I'm saying? The converse is also true. Let's say that you have, say, a car, okay? And the car is moving with some velocity, say 55 miles an hour, okay? And on the road. And let's say there is a stoplight, ahead, there is some stoplight there, and what happens is that the driver pushes on the brake. Well, what do the brakes do to the car? What it does, it changes the state of motion of the car from the state of moving 55 miles an hour to something lower than that, say 0, maybe to stop the car, or maybe to lower the speed to, say, 25 miles an hour or something like that. And the brakes is a form of motion. We call it friction. Okay, friction is a force. So what happened here is that the car was in the state of motion of 55 miles an hour, and then once you applied the brake, which is the action, the force, what happened? The car's state of motion have changed. You see what I'm saying? So that's basically what the force does. Got it so far? Okay. Before I move that's basically the subject of this chapter. But before I go any further than that, I want to talk about Newton's 3 laws of motion. Three laws of motion. I'm going to start with the first law. I'm going to do some writing here. I'm not a big fan of writing with the stylus pen, but I have to do it. So the first law, basically, I'm going to write it in my own way. It's not different from the book. Just the book writes it differently. And anyway, I have my own way of explaining it. So the first law says the following. Bodies that, let me just write it down and I'll explain it to you. Bodies at rest remain in the state of rest. And then the next sentence, and bodies in motion remain in the state of motion in a straight line unless they are compelled by a force, to change the state of motion. To change their state of motion. That's basically the first law. Let's read it together. What it means is the following. Let's go back to my first example. I'm going to redraw it. Let's say we got that book sitting on the table, right? Here is the book. Here is the surface of the table. And the book is at rest. Let's read the first sentence. It says, a body at rest, or bodies at rest, remain in the state of rest. Okay. I mean, that's kind of a common sense. If you have something at rest just sitting there minding its own business, it's just going to stay there. You know? Now, if you have something in motion, moving, okay, as long as there are no forces on it to change the state of motion, it will continue going in the state of motion. That's basically what it said. Bodies in motion remain in the state of motion. Why? Because, well, there's no forces on it. Why would it stop? In order for it to stop or to change the state of motion, there has to be a force. As long as there is no force on it, it will continue in the state of motion, specifically in a straight line. Okay? Unless they are compelled by a force to change their state of motion. So basically what it says here is basically what we have just said. The force changes the state of motion of the object. That's basically what it says. Got it? Okay. More on this law later as we start doing applications. The second law, let me talk about the third law first. And I'll come back to the second law, because the second law is a mathematical law. The third law basically says, and I'm sure you've heard of it before, for every action, there is a reaction. Action equals in magnitude and opposite in direction. Okay? What that means is that, a very simple example. Imagine that you punch the wall. Let's say there is a concrete wall in front of you, and you punch the wall. What will happen to your knuckles? It's going to hurt, right? You have your fist, and then you hit the wall with your fist hard. It's going to hurt your knuckle. Well, why did it hurt your knuckle? The wall didn't hit you back. Well, actually it did. Okay, so basically for every action there is a reaction. It's basically, if I hit the wall, the concrete wall with my fist, the wall will hit me back with the same force that I hit it with, but in the opposite direction. But it is exactly the same. You see what I'm saying? There are more application to that, especially, for example, your weight. We're going to talk about weight in a minute. But that's basically what it is. For every action, there is a reaction. And those two interaction are equal to each other, except they are opposite in direction with each other. Okay, but they are equal in magnitude. These are two vectors. So they are equal. So here is the... here is say the action, and here is the reaction, whichever action or reaction. Let's say this action, and that's reaction. And they are opposite to each other, but they are equal in magnitude. So in other words, if this is F, the reaction, let's say the quantity over to F vector, let's make it minus, this will be the F vector as positive. Okay, where the magnitude of it is exactly equal to the magnitude of this vector. Put a minus there. You see what I'm saying? So they are equal in magnitude and opposite in direction. You got that? Okay. More on it again later. And then the third law, which is the most important, it comes really as a consequence of the two laws. The first law is called the law of inertia. Objects at rest remain at rest. Objects in motion remain in motion unless they are compelled by a force to change their state of motion. And then you have the third law. For every action there is a reaction. And then you have the second law. It's a mathematical law. It says that the force, or rather, all the forces, the sum of the forces on an object, it gives you what is called a kinetic reaction. Okay, and this kinetic reaction is the product of the mass times the acceleration. So basically, sigma F equals ma. And remember, the term ma, we refer to it as the kinetic reaction. Okay? All right. Before I go any further, just here is a question. What is the unit of the force? Well, we can extract the unit from this formula. It says F in its simplest form. F equals ma. We know that m is the mass, right? And the mass has a unit of kilogram. I'm going to put a bracket to indicate units. And of course, we know that the acceleration has a unit of meter per second squared. So meter per second squared. And there we go. The unit of the force is kilogram meter per second squared. Okay? That's the unit of the force. Rather than writing this whole unit every time, there is a shorthand unit which we call it the Newton, big N. Okay? So the Newton is the unit of the force. And what is the Newton? It's kilogram meter per second squared. Get that? Okay. Now, of course, these are units in the SI system. We talked about the SI system in Chapter 1. Okay? Now, in the U.S. customary system, for example, if you are an American engineer and you're dealing with forces, say you're building a bridge or whatever, it has to do with force or weight or whatever, American engineer would use the unit of the force to be the pound. Okay, the pound. For example, if you weigh 150 pounds, what does that mean? It means you are pushing the earth or the ground with a force of 150. Okay, that's the meaning of that. So pound is a unit of force in the U.S. customary system or the imperial system. You get that? So it's either Newton or pound, depending on where you live. For example, in science, of course, we use the Newton. Now, here is something. Remember, I told you about this is just a little trivia for you. Remember, I told you that there is the SI system, and it's divided into two subsystems. One is called the MKS and the CGS. Remember that? And the CGS is centimeter, gram, second, and the MKS is meter, kilogram, second. Remember those things? And, well, here is a little trivia for you. So what is the unit of the force in MKS? Well, it's Newton. We just said that, right? Here, look. It is kilogram, meter, second. This is obviously MKS, so therefore the unit of it is, the unit of the force is Newton. So what if I am a chemist, for example, or a geologist, whatever, and I'm using a CGS system, which is, or a biologist for that matter, centimeters, gram, and seconds. So I can't use Newton. Newton is MKS. So what is the unit of the force in CGS? Ask your biology professor, maybe he knows or not. It's called a dyne, believe it or not. Most people don't know that. And it says the symbol big D, the dyne. If you, in other words, if you are using CGS, you cannot use the Newton or the pound. You have to use the dyne. Now, if you're an American engineer, US, which basically that will be feet, slug for mass, correct? That's for length here. The slug is for mass, and the time is for second, the same thing for time. Well, what about the force? As we said, it is force. It is the pound. You see what I'm saying? See the differences? Okay. Anyway, all right, moving on. I'm looking at my notes on the book here. Just want to make sure I didn't miss anything before I start doing some simple problems. Oh, yes. There's something else. The two more concepts I want to talk about before we do problems. One is called the normal force. The normal force. There will be 2-3 problems from the homework that deals with the normal force. So what is a normal force? A normal force, okay, the word normal, okay, in mathematics, it means perpendicular. I don't know if you know that or not. There are 3 words that describe the word perpendicular. Normal, perpendicular, and orthogonal. It's kind of nice to remember them. Those are all these words describe the word perpendicular. Okay, so a normal means perpendicular. When I say a normal vector, it means a vector that is perpendicular. Well, perpendicular to what? Perpendicular to a surface. Okay, so if I have a surface, here's a surface. Okay, surface of the table, for example. And let's say I put a book on it right now. I just put the book on it right there. Okay, and I ask the question, how many forces on the book? Well, there is the weight of the book, correct? Let's call it W for now. Small letter W. Let's say the weight of the book. The weight is a force, you know, but pushing on it with some, let's say the book is, say, 5 pounds or something. So it's pushing on the surface of the table. However, go back to Newton's third law. What does Newton's third law says? Newton's third law says, for every action, for every force, there is a anti-force or a reaction, a force opposite to it. So if you are right now, as you sit right now on the chair watching this video right now, what you're doing is that you're pushing on your chair, right, with your own weight. Let's say you weigh 150 pounds, so you're pushing on the chair with 150 pounds. Well, according to the third law, it says for every action there is a reaction. So that means there is something that is opposite to your weight, or something is pushing against your weight. And that's what we refer to it as the normal. So the normal is a reaction to the weight. Got that? I mean, not just the weight, for other things. But for this example, the normal is the reaction. Applying Newton's third law, it's nothing but the reaction. So here is the action right here, the weight, right? So the normal in this case, for every action there is a reaction, equal in magnitude and opposite in direction, and we got it the big N. I think your book calls it F sub N with some weird symbol to it. Hold on, let me look it up. I don't like the way your book uses, I'm not sure. When I find it, I'll let you know. I can't find it here. Anyway, so we're just going to call it big N, okay? So the big N means the normal, okay? So what does the normal mean? For now, it is basically the reaction to the weight. You got that? Why? Newton's third law. For every action, the weight, there is a reaction, the normal, okay? And they're both equal, opposite in direction, and equal. Got it? Okay. That's what the normal is. More on it later, especially next chapter. But that's basically what it is. Okay, another thing is the difference between weight, say your weight, and your mass. See the two words? Weight and mass, okay? So what does that mean? Well, think of mass as what, if you ask your chemistry professor or biology professor, what is mass? He will tell you it's a quantity of matter. Makes sense. It basically, the quantity of matter of an object that is containing it is the mass of the object. You see what I'm saying? And that's why we define density to be mass over volume, where the mass here is the quantity of matter. For example, I have the book here, and it's made out of paper or wood material, whatever you want to call it. So that quantity of that wood material, whatever, is what we refer to it as the mass. And it has the unit kilogram or gram. You see what I'm saying? That's what it is. The weight, however, is a little bit different. The weight is how much force you're pushing on the ground, for example. Let me explain. Let's say, for example, here you are. There we go. Oh, forgot your arms. Let's say you're standing on a bathroom scale. Okay, let's say this is a scale, okay? And the scale reads that you are, let's say that your mass is 50 gram, okay? Let's say your mass is 50 gram. You know what? Let's use pounds for now. Sorry, let me use pounds for now. I wanted to say 50 kilogram. That's 50 gram. You are very light with gram. That's silly. Let's assume that your weight, W. Let's say you are 150 pounds. Got it? Assume. Now, all right, that's fine. If I would take you and the bathroom scale, and now I'm going to put you inside an elevator. Here is an elevator. All right? And here you are again. And here is the bathroom scale right there. And let's assume, so you're gonna, and the elevator is not moving. You go in there, close the door, and you look at your weight, and it reads 150 pounds. The same thing. There's no difference. Now you push on the button, and now the elevator is coming down. It's gonna go down. As it's going down, and you look at the bathroom scale, it is not going to read 150. As a matter of fact, it will read something less. Something like, let's say, I don't know what's the number. Let's say 120 pounds. Okay? Now, if the elevator is going up, okay? If the elevator is going up, and you look at the bathroom scale again, believe it or not, it's going to read something a little bit larger. Say 160 pounds or whatever. So what's happening is that your weight is constantly changing, depends on how the elevator is going, up or down. You see what I'm saying? I can show you a different situation like that, but that would be one. For example, if I would, let's say you are 150 pounds, here's another situation. And let's say I'll put you on the moon, and I have you stand up. So here you are here, right here, but now you're on the moon. Well, what's going to happen is that's not going to read 150 pounds. It's going to read something 1/6 of that. It's going to be 150 divided by 6. It's going to read actually 25 pounds, your weight on the moon. The same bathroom scale, the same you, okay? Even though, looking at you, you look the same. You didn't lose any quote-quote weight. You didn't look thinner or bigger or anything like that. You look fine. You look exactly the same. You are the same person, okay? So your mass, in a way, doesn't change, but your weight changes all the time depending on your situation, what situation you're in. You see what I'm saying? So this is the main difference, that your mass, remember, we said mass is a quantity of matter. If that quantity is not changing, it's just going to stay the same. You see what I'm saying? But the weight changes depending on, say, which planet you are in, or whether you are inside a plane moving upward or down, or an elevator or whatever. So your weight's constantly changing. However, and again, more details on it when we start doing problems and next chapter as well. But that's basically the difference between them. That weight, mass in a way is just defined as the quantity of matter that doesn't change. and the weight changes depending on the situation. But there is a relationship between them. And this relation, which is very important, is that the weight, let's call it W, small letter w, is equal to the mass times g, where g here is the acceleration due to gravity, 9.81, if you want to be precise, meter per second squared, okay? That will be the acceleration. So, excuse me. So, for example, let me go back to this person's mass. We said that she is, let's say, 50 gram, I keep saying gram, it should be kilogram, right? So let's say that she is 50 kilogram. What would her weight be? Well, it would be about, if the G is 9.8, which is approximately 10, so she'll be close to 500 Newton. So we're going to go 50, excuse me, times 9.8, using my calculator, 50 times 9.8, and so 490. So she is 490 Newton. Got it? That's her weight. Again, this weight will be different if I would put her inside an elevator going up or down. Okay, it varies. But her mass, 50 kilogram, is just the same, assuming that she didn't eat any extra or she didn't lose any weight, whatever. Okay? Okay, I hope this is clear. So from now on, I like to use when I'm doing problems, when I refer to the weight, I don't like to write W. I just say mg. So I say the mg of the object, which means the weight. Okay? So I use those to get together, indicating it's W. That's just the notation I use. So anyway. Let me start with a simple problem. Yeah, I have example number 1, 2, and 7, and then I'll do 3, 4 problems from the back of the chapter, homework problems. Let me start with the simple ones. Number 1. Let me go back to the hard copy. Just bear with me. It's much easier flipping pages on a hard copy than an e-book. Okay, so on page 103, okay, there we go. We have that. Let me magnify it a little bit. There we go. So, all right, it says here, it said, in our first example, we will consider a very simple application of Newton's second law. Okay, when we say second law, it means F equals ma. Okay, we have a worker here, there's a stick man here, a worker with spikes on his shoes. All right, I guess we don't want him to slip. That's what you mean by that. With spikes on his shoes, pulls with a constant horizontal force of 20 Newton. So he's pulling this, whatever it is, refrigerator or whatever, box with a force of 20 Newton. On a box with a mass, the mass of the box is 40 kilogram. Okay, so the mass of the box is 40 kilogram. And by the way, if you don't have a feel for kilogram, I know because you grew up in this country and you have a more feel for the pound. The kilogram is roughly, let me write it down here very quickly before 1 kilogram is equal to 2.2 pounds, even though there are masses and forces. But that's one way to convert it. In other words, if someone tell you, let's say I'm 40 kilogram, so that's roughly 80 pounds. See what I'm saying? Roughly. I mean, it's a little bit more than that. So if someone tell you I weigh 160 pounds, so that's roughly what, divide that by 2, what would that be? Say 80 kilogram, and so on. You got it? So you just take so 1 kilogram is roughly 2 pounds. So 1 kilogram, roughly 2 pounds. Okay? Roughly. Not, I mean, don't use that for solving problems, but this is just a kind of a mental math. If you are talking to somebody and someone mentions thing, you want to convert pound to kilogram, this is how you do it. Okay? All right. So here, when he said the box is 40 kilogram, and if you got a feel for it, that's about 80 pounds. 80-pound box. All right. So he said, with a mass of 40 kilograms resting on the flat frictionless surface of a frozen lake. What is the acceleration of the box? Okay, all right, let me show you how it works. Always the first thing you need to do is you want to draw what is called FBD, free body diagram. I'll tell you what that is. I think I mentioned it back in the previous chapters. 4.1. Does this look like 4? There we go. Okay. So what you have in here, this is the FBD. Basically, draw the box. Here is the box. And here's the center of the box. And then start putting the forces on it. Okay? So the first force, he said he's pushing the box, or pulling the box, with 20 pounds. So I'm going to put a vector like that, and I'm going to call it 20 Newton. Okay? I don't need to draw the stick man anymore. This vector is sufficient. I don't need the stick man anyway. He's not part of the problem. Okay, now what else do I have? Well, he mentioned the mass of the box, which means what? For every mass, there is an associated weight. Got that? So there is a weight for the box. Here it is. Again, we got to call it W, but I like to call it mg. So far, so good? And for every action, there is a reaction, which is the normal. I don't know if it's important, but we're going to put it here, big N. Okay? And as a result of that, you have the box is moving with acceleration. Since acceleration is not a force, don't attach it to the box. Instead of saying just put it on the outside there, because otherwise you'll confuse or think it's a vector force or something. So just leave it there, just to remind yourself that the box is actually accelerating like that. Now, he's asking the question, what is the acceleration of the box? Here is the question that you want to ask. What's the direction of the acceleration? Well, the direction of the acceleration is in the x-axis. I mean, the box, here is, if I put an x and y here, here is x, and here is y. Obviously, the box is not moving up and down. It's moving along the x in this direction. See what I'm saying? So the acceleration here is in this direction. In other words, the forces that will cause the box to move in this direction are the ones that are in the same direction. So the one that will move the box really is the 20 Newton force. The weight or the mass, the weight of the box and the normal force, I'm not going to move it. Actually, they're going to cancel out because they are opposite and equal, so they're going to cancel out. So the one that is moving in this way. So anyway, I'm going to go like this. So I'm going to apply Newton's second law that says sigma for F equals ma. M here, of course, the mass of the box, and F here in the x direction. How many forces do I have in the x direction? I only have one. And in what direction is it? To the right, what makes it positive. So the sigma F here, the sum of the forces, I only got one, and it's in to the right. So I'll put that plus sign means to the right, equals ma. And the mass here is what? It's 40 kilogram. 40 times A, and that 20, and therefore the acceleration is 20 over 40. So the acceleration is 0.5 meters per second squared. And of course, it's a positive acceleration, so that means it's moving to the right. And that's the end of the problem. Okay? It's a silly problem, kind of. I hope it's too easy for you. We haven't seen the big ones yet. But that's basically what it is. So there was really no need for the weight and the normal here. You see what I'm saying? Because they're not in the direction of motion. All right. Let's do problem number 2, a little bit tougher. Or example number 2, rather. Okay, it's right here. He said in this example, the acceleration is caused by friction force. Okay, we'll come back to this in a sec. A counter attendant, okay, we have an attendant, in a diner shoves a ketchup bottle with a mass 0.2 kilogram along a smooth, level lunch counter. All right? So we have an attendant. He slides or he throws the ketchup bottle along a smooth table, let's say, and the mass of the bottle is 0.2 kilogram. Again, if you want to know how many pounds is that, what do? You multiply by 2. So that's about half a pound, roughly. So 0.2 kilogram along a smooth level launch counter. The bottle leaves her hand with an initial velocity of 2.8 meter per second. Okay. As it slides, it slows down. There we go. We have deceleration. Again, deceleration, we always refer to it as acceleration for both. Whether it's slowing down or speeding out, we just call it acceleration. So as it slides, it slows down because the horizontal friction force exerted on it by the countertop. So you get because of the friction force, eventually it's going to stop, right? Okay, the bottle slides a distance of 1 meter before coming to rest. What are the magnitude and direction of the friction force acting on it? All right. Well, before we do, let me draw the picture first. So what you have in here, here's a bottle. I can draw a bottle. I can draw a wine bottle. How about that? There we go. Close like that. And here is the surface. And so the attendant he uses the term shoves it or pushes it this way, and now the bottle is moving in this direction. So let me just say throws the bottle across table like that. Okay. The data that is given to us, the mass of the bottle is 0.2 kilogram. The initial velocity of the bottle is, what is it, 2.8? 2.8. And definitely there is acceleration there. We don't know what it is. The bottle travels a distance 1 meters, and the final velocity stops. Eventually it will stop, right? That's what it's saying, right? He says, the bottle slides a distance of 1 meter before coming to rest, so eventually it will stop. And what causes it to stop? The friction force. Okay, there we go. Now, I'm going to draw the free body diagram, the FBD of the bottle. This is just a picture of the bottle, how it looks like in motion, instead of saying. Now, here is, I'm going to draw the bottle. Now, you don't have to draw a bottle. You can make it a block, whatever. Okay, I'm just going to draw a bottle because it looks cuter. So here is the bottle. Cool looking bottle, right? There's the label. All right, so here's the bottle, and we're going to ask the question, what are the forces on the bottle? Well, again, we got the mg of the bottle, the weight, and we got the normal, always opposite to each other like that. What else do we have? Remember, once she shoves it, now her hand is no longer touching the bottle. So there is really no force moving in this direction anymore. This makes sense? See, I mean, for example, if I would kick a soccer ball, the moment I kick it, it moves, but that kick is gone. You see what I'm saying? So there is no longer a force in this direction. This is important to keep in mind. So what other forces on the bottle besides the weight of the bottle and the normal force? Well, you have the friction. What is friction? Friction is a force that is always opposing the motion. It's opposite of the motion. What will happen that you get the friction force going this way, and it's a small letter F, we're going to call it. You can call it big F, that's fine. I like small letter F for friction, okay? And there we go. These are the forces on it. Now, the motion is along the x-axis, not the y-axis, and therefore, some of the forces in the x direction equals ma, and of course the acceleration, which is negative, is in the x direction as well. So that's going to be like that with a minus sign. Don't forget that minus sign because it's decelerating. But believe it or not, this minus sign will come out automatically. I'll show you in a second. So now, if I want to put in all what I have in the second law here, it's going to be minus F, correct? Because it's in the opposite direction, equals MAX. I know the mass of the ketchup bottle. It's 0.2 kilogram there, so I can plug it in. No problem. But I still have two unknowns, the acceleration and the friction. I'm going to remove the AX here just because it's understood, just a redundancy. I don't need it. So I still need to know what the acceleration is in order for me to know what the friction is. Well, he gave me enough information here, and I know kinematics to get the A. I'm going to use the second kinematic equation, this one. V squared equals V naught squared plus 2ax. Remember that? And of course, the final velocity of the ketchup bottle is 0. Eventually it stops, right? And so I have 0 equals v naught squared plus 2ax. And I'm solving for a, so that's going to be minus v naught squared over 2x. So that's minus v naught is 2.8. Go see it upstairs, up there. Over 2 times x is 1. And now I can calculate that. And when I calculate it, I get, I hope you're calculating things with me, divided by 2, answer 3.92 with a minus. So in this case, I have A equals minus 3.92 meter per second squared. Does this minus sign bothers me, or it's a good minus sign? It's a good minus sign. I actually expected it. I was hoping for a minus sign. Why? Because the object here obviously is decelerating, so I would expect it to be a negative. So the mathematics took care of it. I didn't even impose a minus sign. Just the mathematics gave it to me. So there we go. So I have here that. Now, once I have it, now I can just easily go back to my Newton's second law and plug in the acceleration and the mass, and I get the friction, and I'm done with the problem. You see what I'm saying? So back to the second law. Let me move that minus sign here, so it becomes F equals minus ma, because I'm interested in the friction. That's minus, what's the mass? 0.2 times the acceleration, I just got it, 3.92. And then we would calculate that, and that will give me, again, we're getting the magnitude here for the friction, times 0.2, answer is equal to 0.784 Newton, okay? Now, this is the friction F, but since the friction F is a negative, at least from the drawing, so I can go like this if I want to the left. You see what I'm saying? But there is nothing special about that, because see, I could have drawn this ketchup bottle to look like that. Here it is, very quickly, where I shoved it, the waitress or the attendant shoved it in this direction. In this case, the friction force would have been positive. You see what I'm saying? So this is all, it depends on how you draw it. What counts is what is the quantity itself, this one. You see what I'm saying? Okay. Good. All right. Let's do something a little bit more complicated. Example 4.7. He goes on about, and if you flip the pages after that, he talks about Newton's third law, the difference between mass and weight. Please take the time to read them. I mean, I talk about all that stuff in briefly, and then he talks in section 4.6, the free body diagram. He goes on about that, and then there are, I'm going to do example 4.7, maybe 4.8. Did I do 4.8 here? I'm not sure. Anyway, I'll do 4.7 for now. That's on page 112. There we go, right here. He says, let's apply our problem solving strategy to a system in equilibrium. Okay. Now equilibrium, that means all the forces on it are equal to 0. That's a big subject. We're going to talk about it later. Okay. He said to improve the acoustics in an auditorium, a sound reflector with a mass of 200 kilogram is suspended by a chain from the ceiling. What is its weight? What force, magnitude, and direction does the chain exert on it? What's the tension in the chain? Assume that the mass of the chain and so on. And if you go to the next page, you see the picture of this thing. Right there. So you get this reflector, just call it an object, whatever it is. I have no idea what he's talking about. But let's say this is a block of wood or whatever. And then you get this chain like that. Okay, I don't like the drawing because it gives you an impression it's a spring. But, okay, let's say this is a chain right here, and it's just sitting there, and it's just sitting there, it's not moving, okay? When something is sitting and it's not moving, we call it the system is in equilibrium. Okay, I'll elaborate on it in a minute, but we're going to talk a lot about equilibrium later in the next chapter. So anyway, he's asking what is the tension in the chain. Let me make a drawing of that. Uh, 4.7. So what you have in here, here's the ceiling, here is the chain. I'm just going to draw a straight line, and here is that object he called a reflector. There it is. And it's just sitting there, that's it. That's basically the whole FBD, the free body diagram. Let's go back and answer the question he's asking. There we go. He says, what is its weight? Okay, so what is the weight? Okay, he says the mass is 200 kilograms. So the mass here is 200 kilogram. Well, what's the weight? The weight is just mg, right? So that's 200 times 9.8. That's simple, really. And then you just plug it in. So that will be 200 times 9.8. Answer 1960 Newton, correct? That's the weight right there. Okay, that's the first part. Okay. Oh, there's no parts. Anyway, okay. So what is its weight? What force, magnitude and direction, does the chain exert on it? Okay, well, before we do that, let's draw the vector, the free body diagram. Well, what are the forces here? Well, we got the weight right here, mg, right? Now, let me ask you this question. Do we have a normal? You can pause the video and think about it. And the answer is no. Why? Because remember, normal comes from what? Comes from a surface. If this block is sitting on the surface, here's the surface. Okay? The surface pushes on the block with a normal, where this is the weight. But there is no normal here. There is no surface where the block is pushing against. So therefore, there is no normal. You get that? So make sure that normal comes from a surface. And we said that the word normal means perpendicular. Perpendicular to what? To the surface. Remember that? So if there is no surface, something like hanging in the air like that, there is no normal. But there is something else that replaces it, and that is tension. The tension is basically in the string itself. You know, the string is tight. Why is it tight? Tight because the weight is pushing on it. So it's tight, and there is a tension. I like to call it big T. I think your book calls it big T as well. Okay? But that's not normal. That's just a tension in the string. All right? And is the system moving? No. So that means acceleration 0. So now if I go back to Newton's second law, F equals ma, of course in this time we're going in the y direction, not in the x direction, as you can see, right? There's no motion in the x, if there is any motion. I mean, all the action here is in the vertical direction. So you can say, if you really insist, you can put y's there. Okay? And since there is no motion, there is no acceleration, guys, right? So this thing is 0. So we say sigma f equals 0. This mathematical statement is called the condition of equilibrium. Very, very important statement. So when you say the word equilibrium, if someone asks you what is the word equilibrium in physics, you just say sigma f equals 0. All the forces on the object sum up to 0. I'll give you an example before I move any further with this solution. Let's say right now you're sitting on the chair, right? Or in the bed or a mattress or whatever, okay? So let's say you're sitting on the chair. Here you are. I'm just turning you into a block. Here you are. Sitting on the chair. Are you in equilibrium? Are you moving up or down? No, you're not moving. You're not hovering in space or anything like that. Why are you in equilibrium? Because here is your weight. And because you're pushing on the chair or the mattress, you get the normal, just like this picture. So here's some of the forces equal to ma, but that ma is 0. Remember, ma means motion. kinetic reaction, accelerated motion. Okay, so as long as you're at rest, this thing is 0. So in this case, sigma f equals 0. You are in equilibrium. Once you see sigma f equals 0, that means equilibrium. And then you just go normal minus mg equals 0, right? The normal is up, that positive. Minus mg going down. And then we have move the mg to the other side. So n equals mg, which I already know. But I have just proved it to you. You see what I'm saying? So that's really the meaning of normal equilibrium. Excuse me. We'll talk about equilibrium, like I said, in the next chapter in more details. But that's basically what it is. Okay, going back to our problem. So here we have sigma f equals 0 in equilibrium. We have just derived it because the system is at rest. So therefore, acceleration is 0. So now, what are the forces? Well, plus t minus mg, right here, sigma f, equals 0. So I have plus t, plus means up, minus mg means down, or left, equals 0, and therefore the tension is equal to mg. Okay? All right. So what is, he says here, let's go back to the question. What is the tension in the chain? Aha. Well, I know what the weight is. What is the weight? We got it, 1960 or something. What force, magnitude, and direction does the chain exert on? Well, he's really talking about the tension, upward. What is it? Lost the picture. Oh, there it is. So we have the tension upward. That's the force he's talking about. And what is it equal to in magnitude? So the direction is upward. And what is the value of that tension? Well, the tension is equal to the weight, and the weight is equal to 1960 right there. So the tension is 1960. You said magnitude and direction. There it is. Got it? What is the tension of the chain? And so on. Okay. One more problem before I do one more example, that is. I want to do example 4.8, so we'll finish the bulk of the examples in the book. I'll do it quickly. Okay, it's gonna, I think it's on the same page. Yes, it is. Scroll down. What? Oh, next page, sorry. Oh yeah, I forgot. This is a continuation of the previous example. He said, now, suppose the mass of the chain in the previous example is not negligible. Okay, so we've taken into consideration the mass of the chain itself. The chain is heavy, but is 10 kilograms. So it's 10 kilogram chain. That's a really heavy chain. That makes it, what, 20 pounds, 22 pounds. Again, let's find the forces on the chain. Okay, so how do we do that then? Well, let's draw the diagram again. See, here we assume the chain, the mass of the chain is massless, or really, really light compared to the big massive block here, the reflector. But now we want to take the mass of the chain into consideration. Okay, what that means is this. So if you have a mass, then you have a weight. Remember that. This is very important. When you have something that it has a mass, no matter how small it is, it has weight. Got it? So in this case, if I draw the same free body diagram that I had, here is the chain, here is the block or reflector, whatever, and then this is the weight, M for the reflector. I'm going to call it the reflector R, MRG for the reflector. Okay, the one we did here. Okay, this is the same one. That's the reflector. I didn't put an index on it because there's only one mass. But now, because we have two masses here, and then I have the tension in the chain. It's all, by the way, tension, guys, always out of the body. Never put tension into the body like that. Never. Okay, tension is always out of the body. So if you're confused, what is the direction of the tension? It's always out of the body, out of any body. Okay. And then we have now a new weight, which is what? The weight of the chain. So I'm going to call it MCG. C for chain, that is. See what I'm saying? That's it. That's the only difference between the two problems, is that I have added the mass of the chain. Now you can put the mass, I know you may say, well, I don't like it putting it here. That's fine. Here, let's take it out. Yeah, would it make you happy if I put it here because the mass of the chain? So I'm trying to put it here. Like that. That makes you happy? Because that's the weight of the chain, so I'm going to put the weight right on the chain. Fine. But I'm going to shift this vector here just for convenience. You see what I'm saying? That's the beauty of free body diagram. So I'm just going to put it here. I'm trying to erase the darn thing. There we go. Okay, so that's basically what it is. All right, so now I'm going to use Newton's second law, sigma F equals ma. Of course, the system is in static situations. Static means ma equals 0. So what are the forces? T, positive, going up, minus weight of the chain, minus, sorry, I'm going to draw it again. This is not, doesn't look pretty. So I have here plus T minus weight of the chain minus weight of the reflector equals 0, equilibrium. See that? And that's about it, really. He wants to know what is the tension in this case. Would the tension be more or less? Should be more, right? So in this case, I have tension is equal to weight of the chain plus weight of the reflector. And then just add them up together. You can put G as a common factor if you want to. So the mass of the chain is 10, plus the mass of the reflector is, forgot, what is it? I forgot. What is this, the mass of the reflector? 200. And then we just calculate that. So that's going to be 9.8 times 210. I have my calculator. 210 times 9.8. Answer 2050. And there we go. We have, since we are considering the weight of the chain or the mass of the chain, in this case the tension will be a little bit higher. So it was 1960 to what is it? 1960, and now it is 2050 because we are considering the weight of the chain. Okay, good. That's basically it. I'm done with this chapter. The chapter is a little bit short, so let's do some problems here. I'm looking at the homework. I already solved some of those problems in my notes here. I want to start with an easy one. The harder ones are the last. The harder ones are the. I'm sorry, bear with me. There we go. The harder ones are number 45, 46, 48. A little bit. Maybe I can do those, but let me do something easy first. Oh yeah, I like number 18 actually. It's pretty cool. I like astronomy problems, kind of astrophysics, astronomy. This one is one of them. Let's go to the problems. Number 18, I'll start with that. Chapter 4. We'll go to chapter 5 and move backwards. Oh, I think I know the number. Hold on. I keep forgetting this book. You can actually go very quickly. Number 18, page 118. Right there. See it? Okay, let's do that. And then we'll do something harder than this one. But it's kind of a cute problem. It says right there, it said at the surface of Jupiter's moon Io, okay? Jupiter has 4, I think it has like 16 moons, but there are 4 major ones: Io, Callisto, Europa, and Ganymede. So one of the moons is called Io. He said the surface of Jupiter's moon's Io, the acceleration due to gravity is 1.81. This is basically what, this is the G value on Io. So the G value on Io 1.81 meter per second square. I'll tell you in a minute what that means in a second. Okay. If a piece of ice weighs 44 Newton, so we have a piece of ice weighs, which means the mg of that thing is 44 Newton. You get that? Okay. At the surface of the Earth. Aha. So this G is what? Earth. Okay. The symbol of Earth in astronomy is a circle with a cross in the middle. That's Earth. I like to use the symbolism. For moon, it's just a circle. And for the sun, is a circle with a dot. Kind of a cool symbols. You can, just, for example, if I say the radius of the Earth, radius of the sun, or radius of the moon, the distance between the Earth and the sun, see what I'm saying? Those symbolism are used in astronomy, and I find them kind of cool notation, so I'm going to use them here. So he said the weight of the ice here, the weight of the ice on Earth, so that means this G is not for Io, but it's for the Earth. So I want to remind myself. How do I know that? Well, that's what he said. He said, look, he said, if the acceleration due to gravity is that, okay, if a piece of ice weighs 44 Newton on the surface of the Earth, which means the mg, the G here is what for Earth. Now he's asking, what is its mass on the Earth's surface? Oh, okay, what's the mass on the Earth's surface? Well, remember, mass doesn't change. In other words, the mass of this ice block on Io, or Jupiter, or the Sun, or the Earth is the same. If it's 2 kilograms, it's 2 kilograms everywhere. The weight changes because G changes. You got that? Okay. So now he wants to know the mass. Well, the mass on Earth, well, I know that. I just use this formula right here and solve for mass. So M in this case is going to be 44 over G on Earth. And G on Earth is 9.8. So that's 44 over 9.8. And I can get the mass of this thing. Answer 4.5, 4.49. Let's make it 4.5 kilogram. Okay. All right. B. What are its mass and weight on the surface of Io? Aha. Well, on Io, this is on Earth, remember. On Io, the mass on Io is what? 4.5 kilogram. Mass does not change. Got that? The quantity of matter doesn't change regardless of where you are. Inside the elevator or in Jupiter or the Sun or whatever. It does not change. But the weight on Io, which is mg Io, let's call it that, sub I don't know what the symbol of Io. So in this case, it's going to be 4.5 times G for Io, which is what? 1.81. And then you get the answer, 1.81 times 4.5, answer 8.1. 8.15, how about that? Newton. Okay, so that's the weight on Io. Notice the difference. See what appears to be, so look at that, the weight of the same ice cube on Earth is 44 Newton, but on Io, the same ice cube is 8.15. So weight changes because G is different, but the mass does not change. You got that? Okay. And I think that's it for this problem. All right, let's do something harder. You know what? Let me do number 39 first. Oh, I know. Let's do 30. 38 is harder, actually. I think some of you are going to find it harder. Number 38. Let me do 38. I'm not going to do 39. You should be able to do it. 38, and then I'll do 45 or one of them. Okay, 38. Let's do 38. There it is right here. It says you walk into an elevator, okay? step onto a scale and push the down button to go directly from the 10th floor to the first floor. Those floors are not important. But basically, what it's saying that you walk into an elevator, you stand up on a scale, okay, bathroom scale, and then you push the elevator down. Now you're going down. Got that? You also recall that your weight is 625. Okay, so you already know before you walked in that your weight is 625 Newton. Okay. Start each of the following parts with free body diagram. All right. A. If the elevator has an initial acceleration of 2.5, okay, this is the acceleration of the elevator, what does the scale read? Now remember, you're going down here. Is that what I'm saying? All right. Okay, let's draw first the elevator, then the free body diagram in a minute. So let me just show you how the picture look like. Here you are. Here is the can't draw it. This is the bathroom scale. There we go. And the elevator, oh, this is the cord of the elevator. We'll assume it's a classic elevator. Most elevators, they actually look, they work like a train. You know, they got those wheels and a train track, a railroad track here. Instead of saying most elevators work that way. But a classic elevator has a cord. But anyway. All right, and so the elevator is going down this way from the 10th floor to whatever, to the first floor. And your weight before you walked in is 625 Newton. That's just your weight. Okay. Part A, he says, if the elevator, he said, look, if the elevator has an initial acceleration of 2.5, it'll be going down, so it's going to be a minus sign. So the acceleration here is minus 2.5 meter per second squared. Remember, this minus sign means direction is going down. It's not deceleration. Okay, it's just direction is going down. Okay. What does the scale read? You think it's going to read more or less? I think it's going to read less. You're going to be lighter. Okay, but let's prove it. Let's prove that. So here, the minus sign here means down. Let me just remind everyone. Okay, and how does the scale, since you're standing on a scale, on a surface that is, here is you. This is you right here, okay? This stick person here is right there. I'm going to turn it into a block, got it? So what are the forces on it? Well, you get the weight of the person, and since it's sitting on a surface, the surface of the scale or the elevator, so there is a normal going this way. It's pushing against it. So you got to have that normal. Okay, and then the acceleration going down this way. See what I'm saying? So, what does the scale read? Let me tell you what it reads. And I want you to maybe pause the video and think about it after I tell you what it reads. It basically reads what the normal vector is. Okay? In other words, this normal right here is what the scale is reading. Remember, normal is what? Force against the surface, which is basically what the scale will read. The weight is not, it's the same. Let me show you. Again, all the motion here is the y direction, so I don't need to say sub y or whatever. I mean, I can write it this way, but that's just a redundancy. There is no motion in the x direction, so I'm just going to remove those y's. Okay, so what are the forces here, guys? There are two of them. The normal, n minus mg equals ma, correct? MA right here. And of course the A for us is this number here. Okay, let's plug it in. Again, what does the elevator read? It reads the value of the normal. This is very important. Keep that in mind. If you say, well, what do we need the normal for? Well, that's exactly how much force you're pushing on the surface. And that's what the scale is feeling. It's feeling your normal. Got it? Okay. So basically, if I solve for this n, that's basically what the elevator is reading. That's basically what the elevator is saying. How much do you weigh with that motion? You got that? So, okay, so I'm going to solve for n then. N is equal to, it's not looking, n equals to, just solve for it, so you move the mg here. That's going to be ma plus mg. And then you put in, let's take m as a common factor, like that. So the m here, oh, I forgot to bring what the m is. Hold on, let me just let me go back. Sorry. He said in the problem right there on the top, he said your weight before you walked in is equal to 625. So I'm going to write it down here because I need to find the mass. So given mg is 625 Newton, therefore the mass is 625 over 9.8, right? Divided by g. So the mass, I need to find the mass. So use my calculator. Again, the math doesn't change. So we go 625 divided by 9.8, answer 63.8 roughly. Okay, so you are 63.8 kilogram. There we go. That's the mass of the person in the elevator. Now I go back to here. So therefore the normal is going to be 63.8 times the acceleration. What's the acceleration, guys? Don't forget that negative, because the negative means you're going down. If you're going up, you're going to put positive. So it's going to be, you're going to be subtracting it from 9.8, so that's negative 2.5 plus 9.8, and then we calculate that. So that's going to be 63.8 times 9.8 minus 2.5, answer 67.3, and then you multiply those two together. 63.8, answer 465.7. 465.7 Newton. There we go. So the elevator is going to say you weigh not 625, but 645. Oh, excuse me, 465.7 Newton. Got it? Okay. Next, this is part A for the problem. This is all part A. There it is. Let's do part B now. Okay. He said, what does the scale read after the elevator reaches its final speed as it heads to the bottom floor? In other words, what does the elevator read after you stop? I mean, it just stops. Okay, you reach the bottom floor, the elevator stops. You're still standing on the scale. What does it read? Well, obviously, it's going to read 625. You go back to your normal weight, right? Is that okay? I mean, it makes sense. Can we prove that? I mean, I can, without looking at anything, of course it's going to read my old weight. I started with 625. I go in the elevator. I became lighter because I'm moving down. If I'm moving up, it's going to go higher. And the reason it's going to go higher is because this negative sign here is going to be positive. So you're going to be adding 9 to 9.8. It's going to be a bigger number. So when you stop, when the elevator stops here, well, it's just going to go back to 625. That's what it's going to read. In other words, the normal is going to read 625. Can I prove that? Yeah, you can prove it. All I need to do is use the same formula, this one right here, sigma f equals ma, where there's no ma anymore. It stopped. Look. So after elevator stops, sigma f equals ma, but the ma is 0. So I'm basically equilibrium, that is. I have that. And so I have what? Here you are. Here is your normal. Here is your mg. And acceleration is 0. That's your FBD right here, right? So it's just going to be n minus mg equals 0. Normal is equal to mg, but mg is 625. And there we go. Simple. That's it. Got it? Okay. All right. I'll do one more problem, and then we'll call it a day. I'll do those astrophysics problem. Number 48. Yeah, 48. I have the word beside it says nice. I guess I liked it. I don't remember. I Last time I solved it was last year. Let's go to it. It is homework. Okay. 48 right there. Okay. It says, let's make it bigger. This is the last page. There we go. Okay, it says extraterrestrial physics. You have landed on an unknown planet. Okay? Newtonia, we're going to call it. And you want to know what object will weigh there. You find that when a certain tool is pushed on a frictionless horizontal surface by 12 Newton force, it moves 16 meters in the first 2 seconds, starting from rest. Okay, so you're on a planet. You don't know the value of G on that planet. That's really what he's trying to tell you. Okay, you don't know the value of G. And so you want to do some experiment to find the value of G. So you take a block and a certain tool, and then you push it on a frictionless surface, and with a force of 12 Newton, and you discover that this block moves at a distance 16 meters in the first 2 seconds. Now, why is he saying that? Well, hold on a minute. Starting from rest, okay? Next, okay, what else? Okay, you've done another experiment. You next observe that if you release this tool, that same tool, from rest at 10 meters above the ground, so in other words, you go up to a cliff or whatever, you take the same tool and you throw it at from a distance of 10 meters above the ground, and with your little stopwatch, it takes it 2.58 seconds to reach the ground. Now he's asking, what does the tool weigh on Newtonia, and what would it weigh on Earth? Okay? Really, what he's asking for, what is G on Newtonia, and what is the mass of that tool? Okay? What's G? I mean, if you know G value of Newtonia, you're done. You know the weight. The weight is mg. But you need to know the mass as well. So basically what he's really asking for, what is the mass of that tool on Newtonia? Oh, it doesn't matter. Mass doesn't change. What's the mass of that tool, and what is the G value on Newtonia? You got it? You can pause the video and read it slowly. Make sure that you understand it. It's very important that you understand the problem, any problem, before you solve it. All right, let's see how it works. I'm on the edge of the screen here from my perspective. I'm trying to erase this stupid thing. There it is. All right, let's write down what's given to us. So here is the tool. We're going to turn it into a block again, the FBD, free body diagram. Then if I push this tool with a force F equals 12 Newton, it's going to move a distance x equals 16 meters, okay? And for a time of 2 seconds. And the initial velocity is 0. That's what he said, look. You find that when a certain tool is pushed on a frictionless horizontal surface of 12 Newton, it moves 60 meters the first 2 seconds from rest, starting from rest. Okay? So these are the information. That's part number 1, if you will. Why did he give me all this information so far? No clue. But he gives me this information. Okay? Part number 2. I'm acting like it's no clue. Number 2. He says, next, you observe that when you take this tool and you throw it, drop it from a height of 10 to the ground, it takes 2.58 seconds. So here is this another picture for you. Here is the height, free fall thing, you know what I mean? Of 10 meters. Did you say 10 meters? I'm sorry. Yeah. So from a height of 10 meters, again, we're doing free fall kinematics here. Here's the tool. And it crashes here. And it takes it a time of 2.58 seconds. Now, I'm going to ignore what he's asking for. I'm asking this one. What is G on Newtonia? I'm going to call it G sub n. And what is the mass of that tool? Okay? If we find this, we're done with the problem, really. So I want to find G on Newtonia and the mass of the tool. Well, I have I've done two experiments. Experiment number 1, experiment number 2. And let me work with experiment number 1. You know, the force when he pushes the tool along the distance. So here it looks like kinematic equation. You know, I can use kinematics to solve for it and see if I can get something out of it. Watch how it works. For part 1, I know that since it's given, time is given, distance is given, I'm going to use the third kinematic, which is this one. X equals V naught t plus 1/2 at squared. Remember that? Okay. The initial velocity is 0, so let's go to 0. So I have x equals 1/2 at squared. I have the time right there, and I have the x right there. And what do I get out of it? I'm going to get the acceleration. Do I need this acceleration? If you still not understanding what's going on, bear with me. I'm going to get that acceleration. I'm going to show you why in a second. So if I solve for a here algebraically, it's going to look like this: 2x over t squared. All right? Plug it in. So I have 2 times 16 over the time. He said the time is what? 2 seconds. So that's going to be 2 squared. So if I do that, that's going to be 32 over 4. Is that right? So we have 32 over 4 8. I should have known that. That was dumb. I actually used the calculator for it. Anyway, so we have here the acceleration 8 meter per second squared. Now, what do I need that for? Again, you can pause the video and think about it. Let me show you why. Go back to Newton's second law. F equals ma. He said the force is what? Look at that. He said the force is 12 Newton. I have just gotten the acceleration. I can find the mass. See that? See how cool is that? So it's going to be 12 equals the mass times 8. Therefore, the mass is 12 over 8. So I have 12 divided by 8, 1.5. So there we go. I got the mass of the tool. So that's why he gives me all that information for part 1. He doesn't want to tell me that, but he said, well, you can find the mass with that. There we go. I got the mass. Isn't that nice? Okay. Part 2. He gives me free fall information. He said if I throw the same tool, mass 1.5, from a height of 10, it's going to take it 2.58 to come to the ground. Okay, so which kinematic I would use? Maybe I'll use the usual kinematic, you know, the y equals v naught, the one we use all the time. I'm just going to, the default one. T minus 1/2 gt squared, right? And of course the initial velocity is 0, so I have y equals minus 1/2 gt squared, and then the y here is negative 10, right? Minus 4.9, correct? 1/2 times g is 4. Oh, sorry, hold on. I'm doing something really bad here. Remember, this g is on Newtonia when I don't know anything about. Got it? I don't know anything about that. So that's minus 10 equals minus 1/2 g on Newtonia times the time squared. He gives me the time. The time squared is 2.58 right there. So I'm going to plug it in. Squared, and look at that. I can actually find g on Newtonia. See that? So that will give me the minuses cancel out. I end up with 20 equals g times 2.58 squared. I just need to do the math. So g on Newtonia is 20 over 2.58 quantity squared. And then I use my calculator. So it's going to be 20 divided by 2.58 squared. Answer, whoops, up there, and that's equal to 3. Anybody got 3? Let me do it again. Sorry. I got 3 again. So that will be equal to G on Newtonia is equal to 3 meters per second squared. Aha. Now what? Okay, so excuse me. From the first part, I've gotten the mass right here. So I'm going to write it down. And in the second part, I found the G on Newtonia. Now let's go back to his questions. He said, what does the tool weigh, which is the mg, on Newtonia and on Earth? Well, that becomes easy, right? mg on Newtonia is basically, sorry, I should have said it the other way. I'm sorry, I'm getting a little tired talking for the last hour and a half. So we have on Newtonia. So the weight here is mg Newtonia. Mass is always the same, guys. So 1.5 times 3, and that would be equal to 4.5 Newton, the weight of the tool on Newtonia. And then for Earth, that will be mg for Earth, and that will be 1.5 times 9.8, and that'll be equal to 14.7 Newton. And there we go. This is really what he's looking for. Got it? Okay. I think this is it. There are other problems you can work on, but I think I'm going to stop here. And let me know if you have any questions. You can just post them under Ask the Professor, and I'll be more than happy to answer your questions. Have a good week. Bye.